Welcome to the ePathshala lecture series in computer science. We are dealing with the course computer architecture. So today we look at an example for dynamic scheduling. The previous module we looked at how dynamic scheduling can be done using Tomasulo's approach. So in this module we look at a sequence of instructions and see how actually dynamic scheduling happens for these sequence of instructions. And these sequence of instructions will not involve a branch instruction. We will do a clock level simulation of the Tomasulo's approach, so to understand how instructions are issued, how they enter out of order execution and complete execution out of order. So before we get into the actual details of the simulation, we'll just go through the basics of Tomasulo's approach in order to enable you to understand what happens in the simulation. So in the case of the Tomasulo's approach, you know that the hazard detection is done in the reservation stations. The name dependencies, your anti-dependence and output dependence are name dependencies, and they will cause war hazard or a war hazard in the pipeline if not handled properly. Now these war and war hazards are removed here in the case of the Tomasulo's approach by doing a register renaming process. So the hardware does the renaming process by looking at having reservation stations. So there is a mapping between the registers and the reservation stations, and these mappings will help you avoid the name dependencies. And because the reservation stations are distributed, your hazard detection is also done in a distributed manner, and thus war and war hazards are eliminated. And in, in the place of virtual registers, like virtual registers, we are going to use reservation stations, and this overcomes the limitations of the number of physical registers. So this is the architecture of your Tomasulo's approach. Just to recall whatever we did in the previous module, you have a set of floating point registers, you have a floating point of instruction queue. So instructions are prefetched and put into the floating point instruction queue, and they are removed one by one from the floating point instruction queue. So as an instruction is issued, it is removed from the queue and it is issued. And remember that the decoding is done during the issue stage. The issue stage consists of only decoding of the operation and checking for structural hazards. So once the instruction gets decoded, you know what operation is to be done. So accordingly, it is assigned to a particular reservation station. So at the issue stage, you decode the instruction, find out what instruction it is, and accordingly allocate a reservation station entry for this. If there is no reservation station entry available, then it becomes a structural hazard. So you can see the reservation station entry is given along with the functional units. The floating point adder units have a set of reservation stations, 3 reservation stations indicated there as add 1, add 2, add 3. The floating point multiplier divider units have 2 reservation station entries, mult 1 and mult 2. You have a set of load reservation station entries which are called the load buffers. For store instructions, you have the store buffers. So each instruction, when it is issued, the details are given into the reservation station. Operands are already buffered into the reservation stations from the floating point registers. And if some operand is not available, it is dependent on an earlier instruction, the reservation stations will hold information about which instruction is to produce a result for these instructions. And once an instruction gets all the operands, it automatically enters execution in the next clock cycle. It remains in execution depending upon the latency of the instruction, and once the instruction finishes, the result is transmitted on the common data bus. And from the common data bus, the result that is broadcast on the common data bus is given to all the the reservation stations associated with functional units which are waiting for that data, and it also goes to the floating point registers, as you can see, the registers which are waiting for this data. So this is the general organization of your Tomasulo's dynamic scheduler. So if you look at the 3 stages of the Tomasulo algorithm, the first stage is the issue stage, where we get the instruction from the floating point queue. And because it is a queue that is maintained, it is always removed from the top of the queue or in a first come first serve basis. So issue involves a decoding of the operation, and checking for structural hazards. The structural hazard that is being tested for is the availability of a reservation station. So, if there is no reservation station available, then that instruction cannot be issued. And remember that if a particular instruction has not been issued because of a structural hazard, we are strictly looking at an in order issue. So, the subsequent instructions also cannot be issued. So, that is the first stage. And during the issue stage, if operands are already available, you read the operands from the register file and load them into the reservation station entry. If operands are not available, then indicate the fact about which instruction is to produce a result for this particular instruction. All that happens during the issue stage. The next stage is the execution stage. So, the execution stage is when the operands have already become available for the instruction. So, when both the operands for the instruction becomes available, the instruction automatically enters the execution stage in the next clock cycle. So, if it is a floating point multiply instruction, once the reservation station gets filled up with both the operands for multiplication, it automatically is passed on to the multiplier unit. The multiplier unit starts executing, and it remains in execution till depending upon the latency of the instruction. Suppose if you assume that a 10 clock cycle latency for a multiply instruction, it will remain in execution for 10 clock cycles. And once execution finishes, the result is written on the common data bus. That is the third stage, which is called the write result stage, when an instruction finishes execution. Recollect that we looked at a common data bus. So, all the results are published on the common data bus. So, the results that are broadcast on the common data bus go to all the reservation stations waiting for this result. They also go to the registers, the floating point register file, where the result has to be finally written into. And a difference between the common data bus and the normal bus that we have that we are aware of is that in a normal data bus, normally what we do is we send the data and we also give the destination address. We say store this data at this particular address. So, the address is given, the data is given, the data gets written into that particular memory location. Now, here what happens is, in the case of a common data bus, you of course transmit the data, but you also say it is not the destination that is given as in the case of a go to bus, it is the source uh, information that is given. That is, you are saying that the data comes from this particular source. Say for example, if you are looking at a multiply instruction finishing completion, then you say that this multiply instruction has finished operation and the result of this multiply operation is this data. So, it is different from the normal data bus that we are aware of. The CDB is a come from bus and not a go to bus. So, the data as well as the information about the source register. For example, if you assume that you have 4 bits to represent the various reservation stations associated with the functional units, then a 4-bit information which gives the source information and the 64 bits of data are transmitted on the data bus, common data bus. And if any reservation station's entry matches with this source address, then those reservation stations will take in this information from the common data bus. And also the floating point register file, which is maintained in your register result status, which is waiting for the result of this operation, also takes in the data. So, these are the 3 stages of the Tomasulo algorithm. Now, we will go through an example, a simulation, a clock level simulation to understand the basics of dynamic scheduling better. So, we look at an example here where you have 2 load instructions. You have a first load instruction, you have a second load instruction, you have a multiply instruction which is dependent on the second load, you have a sub instruction which is again dependent on the load instruction and also dependent on the second load instruction. You have a divide instruction which is dependent on the multiply instruction. You can see all the data dependencies there. And finally, you have an add instruction which is again dependent on the sub instruction. And you can see the three data structures that are maintained by the Tomasulo's dynamic scheduler indicated there. The main data structure is the reservation station entry. You can see that the reservation station has a name. It has a busy field which indicates whether the reservation station is busy with some instruction occupying it or not. You have an op field, an operation field, which indicates what operation is to be done in the reservation station, and you have two operation to be done in the functional unit. You have the Vj and Vk fields which give you the values for that particular instruction, and you have the Qj, Qk fields which indicate if values are not available, then the Qj, Qk fields will get filled up, indicating which reservation station entry is going to produce this data for you. Recall that once an instruction has been issued to a particular reservation station entry, then the instruction from then on is identified only by means of the reservation station entry. So, that is the unique identifier for the instruction from then on. And this mapping process from your registers, because you are going to read operands from the registers and store them into the reservation stations. So, the mapping from the register file to the reservation station entry does the renaming process and helps avoid all the name dependencies and the associated hazards. So, you have a clock cycle counter which tells you which clock cycle is proceeding. We assume that there are 3 load buffers. The load buffer entries, you know that you need to have an address, you need to have a busy field indicating whether the load buffer is free or not. Of course, we do not have any store instructions here, so the store buffers have not been indicated. So, that is the first data structure which gives you the reservation stations. The second data structure is the instruction status. So, you have a set of instructions, a sequence of instructions from the instruction window, and the status indicates which status the instruction is in the current clock cycle, whether it is in the issue stage or whether it has already completed execution and or whether it is writing the result. Because we have already seen that there are 3 stages in the Tomasulo's algorithm: an issue stage, an execution stage, and the write result stage. So, that gives you the instruction status. That is the second data structure. This is more for understanding purposes. The third data structure is your register result status. So, you have all the floating point registers and an indication as to which reservation station entry is to write into that particular floating point register. So, these are the 3 data structures that are maintained by your dynamic scheduler. You have a clock cycle counter which gives you which is the current clock cycle that is in progress. And you also have a countdown register which tells you how many clock cycles of the latency is over now. Suppose if you have a multiply instruction and it takes 10 clock cycles, how many clock cycles of that 10 cycles are now over. And we are looking at 3 floating point adder reservation stations, and we are looking at 2 floating point multiplier reservation stations. So, that is the assumption. And if you look at the latencies associated with these floating point instructions, we assume that the add and the sub instructions take 2 clock cycles each, the multiply instruction takes 10 clock cycles, and the divide instruction takes 40 clock cycles to execute. Those are the latencies that we assume for this particular simulation. So, depending upon the latencies and depending upon the availability of the number of reservation stations and all that, things will change. All these assumptions are for this particular example that we are going to go through. So, the first clock cycle, when you look at the first clock cycle, you see that the first load instruction has been issued. So, the first load instruction has been issued, that is issued to your, so you decode the instruction, identify that it is a load, and you allocate the load buffer entry load 1 there. And for the effective address calculation, you need the displacement and register R2. So, those values are also stored in your reservation station entry, and the register result status indicates that register F6 has to be written by your load instruction, because the load instruction when the data gets loaded, it has to write into F6. So, it indicates that F6 has to take the data from load 1. All this happens during clock cycle 1. During clock cycle 2, you know that the second instruction, it is a single issue processor. So, the second instruction in succession, so the second load instruction is issued in the second clock cycle. The same things happen here. So, you have the second load entry, load buffer entry being allocated for your second load instruction. The effective address can be calculated using 45 and R3. So, that value is again stored in your load buffer, and in the meantime your first load instruction, assume that the first instruction will move on from the issue stage to the effective address calculation stage. So, when the second load instruction is being issued, the first load instruction will do an effective address calculation. So, the address will be calculated, the address of 34 plus the contents of R2 will be calculated and it will be stored in your load buffer entry. And similarly, because you have already issued the second load instruction, observe that the result register status indicates that F2 has to be modified by your load 2 instruction. Now, during clock cycle 3, you find that you will have to issue the next instruction. But one observation that you can make here is we have issued 2 load instructions. You can have multiple load instructions outstanding, that is because you have multiple load buffers. So, in case if you have 3 load buffers, you can actually have 3 load instructions pending. Here we have only issued 2 instructions so far. So, during the third clock cycle, you find that the third instruction, which is your mull instruction, which is being issued. So, mull instruction is being issued. So, you have your multiplier mult1 reservation station entry. It has become busy now. The mull instruction, the operation is multiplication there, and you find that the operands, there are 2 operands for it. One is an F4, the other one is the contents of F2. F4 is already available. So, you read the contents of F4 and store it into your VK value. But as far as your VJ value is concerned, that is not available. The first operand is dependent on the second load instruction. So, we just indicate in the QJ field that load 2 has to produce a result for our mull instruction. Meanwhile, the load instruction has already finished execution. It had done the effective address calculation earlier. Now, it has finished execution. So, the execution is complete for the load instruction, and you find that your register result status indicates that F naught has to be written by your multiply instruction. So, those are the things that happen during clock cycle 3. Look at the observe the fact that the register names have been removed and they have been renamed with the help of reservation stations when your mult instruction has been issued. So, the operand has already been read from the register and it has been buffered in your reservation station allocated to your mult instruction. That is the renaming process that happens. And during clock cycle 3, you know that load instruction 1 is completing. Now, what is waiting for the load instruction? You do not have any issued instructions waiting for the load instruction. So, you do not have to worry about it for the time being. So, during clock cycle 4, because load 1 had already executed in clock cycle 3, it will do a write back in clock cycle 4. A write back is, recollect that the write back is, it will broadcast the data on the CDB. So, when it broadcasts the data on the CDB, the floating point register which is waiting for it, which will grab in the data, as we have already indicated, F6 will take in the data. It will also, if any reservation stations are waiting for it, it will go into those reservation stations, but here we do not have any reservation stations waiting for that data. So, only F6 gets that data. Meanwhile, load instruction 2 also has finished execution, 3 and 4 it will do execution. So, execution is complete. And the other activity that happens is in clock cycle 4 is the fourth instruction, which is your sub instruction, gets issued. And when sub instruction is issued, observe the fact that you have a reservation station entry allocated for it, which is your add one reservation station entry. The operation is indicated as sub. One operand for that comes from your load instruction. For the sub instruction, the operands are F6 and F2, which comes from both the load instructions. So, one data is already read because the data is already available, it is read and stored there. The other operand has to come from load 2 instruction. So, the QK field indicates that load 2 has to produce the data for this instruction. All this happens during clock cycle 4. You know that in clock cycle 4, load 2 is completing. So, when load 2 is completing, what are the instructions that are waiting for load 2? Both your mull instruction as well as the sub instruction are waiting for load 2. So, when load 2 writes the result, all of them will take the result from the common data bus. So, the multiply gets the data from load 2 and your sub instruction also gets the data from load 2. So, during clock cycle 5, you observe that the common data bus takes in the data, broadcasts the data from your load 2 instruction, which goes into the corresponding reservation station entries, and it is also written into the register file F2. F2 takes the data from the common data bus, which passes on the result of your load instruction. So, the reservation station entries associated with your mul instruction and the reservation station entry allocated to your add instruction, both of them get the operands F0 from the load instruction. Both of these use the data from the load instruction, which is F2. F2 result is produced. So, F2 is a source operand for your mul instruction. F2 is also a source operand for your sub instruction. So, both of them get the data. Look at the counter that has been indicated here. Because the operands have become available now for the mul and your add instruction, the latencies have been indicated there. So, add has a latency of 2 clock cycles and mul has a latency of 10 clock cycle that has been indicated in the example. So, the timer now starts down for your add 1 and the multiply instruction. So, clock cycle 1, both these instructions have already gone through 1 clock cycle execution. Clock cycle 6, you have the 6th instruction being issued. So, 6th instruction is your add instruction now. So, add is being issued. So, add is issued to a reservation station allocated to your add functional unit, which is your add 2 unit. So, that has become busy now. So, the operands, one operand for the add instruction comes from is F8, the other one is F2. F8 has to come from the sub instruction has not yet completed. F2 comes from the load instruction, load 2, which has already completed and written its result. So, you just read it from F2 and store there. The other operand indicates that sub instruction, that reservation station entry has to produce the result. The divide instruction has already been issued in the 5th clock cycle. So, that goes into the multiply 2 reservation station entry. So, all this happens during clock cycle 6. One observation that you will have to make here is we are issuing the add instruction here despite the name dependence on F6. So, if you look at F6, F6 is one of the source operands for the divide instruction which is issued in the 5th clock cycle, and you observe that add writes into F6, that is a destination operand for F6. But you do not have to worry about this because F6, once the data becomes available after the load instruction, load 1 instruction, F6 would have been written by the load 1 instruction, and that operand has already been buffered in your divide reservation station entry, which is your mul 2. So, you do not have to worry about it. So, you are issuing the add instruction despite the name dependency on your F6. So, clock cycle 7, the sub instruction has only a latency of 2. So, the sub instruction already finishes 6, 7, it finishes execution. Nothing else changes here, and add 1 is completing, and because which is your sub instruction. So, sub is completing, what is waiting for it is your add instruction, because the destination operand of your sub instruction F8 is a source operand for your add instruction F8. So, now you look at the latency counter. So, the add instruction has finished execution, the mul instruction has finished 2 clock cycles of execution. So, it is the latency is 8, and in the next clock cycle you will observe that your add 2 instruction will start executing because the operand has become available. So, sub writes in the 8th clock cycle, and the 9th clock cycle you will find that the add instruction starts executing. So, add will take 2 clock cycles to execute. So, 9 and 10 add will execute. So, add finishes execution in 10th clock cycle, and add will write its result in the 11th clock cycle. So, 11th clock cycle add finishes execution. So, the instructions that are still pending are the multiply instruction because it is a long latency instruction, and of course, the divide instruction which is again dependent on the multiply instruction. So, mul has 4 more clock cycles to go, and only when the mul instruction finishes your divide instruction can execute. So, that is the status that has been shown here. So, in clock cycle 11 you will have to write the result of add D. So, clock cycle 11 you write the result of add D, and all these short latency instructions which are quick instructions you find that they complete in this cycle. So, clock cycle 12 there is not anything major happening here. One more observation that you will have to make here is your load buffers, because both the load instructions are already over, the load buffers have already been released. So, it is ready to take an if at all you have another load instruction available, it is ready to taken. So, the busy status indicates that they are free, and similarly your add units are have finished execution and they've written their results. So, the add reservation station entries are also free. So, they are ready to take in other add instructions. Only the multiplier reservation station entries mult1 and mult2 are still holding the operands. In clock cycle 13, again the same thing happens. You have 2 more clock cycles to go. So, clock cycle 14 nothing major happens. Clock cycle 15, you know that your multiply instruction finishes execution. So, the multiply instruction operand became available in 5. So, it starts executing in 6. 6 to 15 it does execution, 10 clock cycles execution. So, 15th clock cycle it finishes execution. 16th clock cycle it will have to write its result. So, when multiply finishes execution, you know that the divide instruction is waiting for it. So, the divide instruction will now take its operands. So, the 16th clock cycle the multiply instruction writes its result on the CDB, which will now go to the reservation station mult2, which has been waiting for that result, which is your divide instruction. So, now your latency counter indicates that because the operands are now available, the divide instruction can start executing, and your latency counter indicates that you have 40 cycles of latency to go for your divide instruction. So, the next clock cycle your divide instruction starts executing. You find that your divide instruction starts executing, and because divide has a latency of 40 clock cycles, it starts executing and it finishes execution in 56 clock cycle 56. It takes 40 clock cycles to execute. So, starting from the 17th clock cycle, because mul finishes in the 16th clock cycle, divide starts executing in the 17th clock cycle and it remains in execution for 40 clock cycles. So, the 57th clock cycle divide finishes execution, and the 57th clock cycle you have divide finishing. So, this is the complete status of all the instructions. This table clearly shows you when each instruction is issued, when they finish execution, and when they complete the execution and write the result. So, we have strictly gone in for an in order issue, we have looked at an out of order execution, and we have also looked at an out of order completion. Two major advantages of your Tomasulo scheme is that one is the distribution of the hazard detection logic. So, the hazard detection logic is not centralized as in the case of the other dynamic scheduling algorithm. Of course, we did not discuss that algorithm, but one of the major drawbacks of that is the hazard detection unit was centralized. Here we have a distributed hazard detection logic, and the CDB transmits the data. Because the data is broadcast on the CDB, even if you have multiple instructions waiting for a single result, all of them get the data, and you find that all of them are also the data is also written into the waiting floating point register. The other advantage is that because of the renaming process that you use, the renaming process avoids your war and war hazards, and instead of using a centralized register file, we use a reservation station. So, you do not have a problem of reading it from the centralized register file. So, these are the major advantages offered by your Tomasulo's algorithm. And of course, because of the renaming process, you have the elimination of stalls for caused by your name dependencies, anti-dependence and output dependence, which will cause a possible war hazard and a war hazard. So, all these are eliminated in the case of your Tomasulo's approach. Of course, Tomasulo's approach has certain drawbacks. The first drawback is the complexity of the algorithm. We have already looked at the organization of a Tomasulo's approach. So, all of us know that it is a very complicated setup. You have a lot of bookkeeping that has to be done in hardware. So, the hardware definitely becomes more complicated than a processor which does not support dynamic scheduling. And if you look at the CDB, you have many associative stores which happen, because the data that is transmitted on the CDB goes to your floating point register file. It also goes to the reservation stations. So, all these will have to do an associative compare, and they will have to take the data if the reservation station entries match. So, there are many associative stores, and also remember that the performance is limited by the common data bus, because each CDB must go to multiple functional units. which means you have high capacitance and high wiring densities coming into picture. And also the fact that because you have only one CDB, the number of functional units that can complete execution in a particular clock cycle is limited to one. Because if more than one instruction finishes execution, then you can't transmit two results on the CDB, in which case you will have to look at multiple CDBs. Multiple CDBs obviously means that you have more logic you will have to bring in, because you are looking at parallel associative comparison stores. So, these are the complexities associated with your Tomasulo's approach, and of course, your non-precise interrupts, because we are not looking, we are strictly looking at an in-order issue, but instructions go out of order execution and instructions also finish out of order. We already have the problem of non-precise interrupts, because with floating point instructions, even with an in-order execution, they will finish out of order. Now, things are worse because we are anyway going in for an out of order execution depending upon the availability of operands, and they will definitely result in an out of order completion, which will give rise to non-precise interrupts. We will handle that in the subsequent sessions. So, to summarize what we did in this module, we have already looked at the Tomasulo's dynamic scheduling algorithm. In this session, we looked at simulation for a sequence of instructions, and we saw how the dynamic scheduler schedules these instructions. We saw that the Tomasulo's dynamic scheduler uses distributed hazard detection logic, and the example shows how the processor does an in-order issue, out-of-order execution and out-of-order completion. So, by just looking at the table, you are able to clearly understand what happens inside the processor when each instruction is issued, in which clock cycle it is issued, which clock cycle it enters execution and finishes execution, when it does a write back. So, all that is it clearly comes through in our clock level simulation. And of course, you will have to understand the fact that it definitely complicates the hardware. The dynamic scheduler definitely complicates the hardware, but it definitely simplifies the compiler on the other end. And also remember the fact that we have not looked at branches at all here. We have just looked at a sequence of instructions without branches. Branches will be handled in the next session. Thank you.